In the previous video, we have shown that the set of all linear combinations is indeed a subvector space of a vector space V. Okay, so let's write here the definition of this set of linear combination. So it is denoted by S with two angular brackets. This is defined as a set as the union of all linear combinations, sums for I that goes from 1 to n, lambda I times vi, such that lambda I are scalars, vi are vectors in S, and n is a positive integer. Okay, I also said that this is the prototype of all the subvector spaces. More precisely, if we consider all subvector spaces in V, so what is V? V is related in the following way to S. So S is a subset of V. V is a vector space. So if we consider all the subvector spaces of V of this kind, basically I exhausted all the possible subvector spaces of V. So any subspace of V is of this form for some S. Okay. Therefore, studying all these subspaces means studying all the subspaces of V, not just a particular kind. Indeed, we have the following result. Notice that if W is a subspace of V, so when we will indicate subspace, we'll indicate some set, some vector space on the left and another vector space on the right, related by this symbol. That means that the one on the left is a subspace, subvector space of the one on the right. If instead we consider this just as a set and not with algebraic structure, then we will denote the inclusion like so, like we always done with for sets. Okay, so this angular sign implies that this subset is included in this vector space with the structure that it has. So if this is a vector space, it means that this is going to be not just a subset of V, but a subvector space of V. Now notice that if W is a subvector space of V, then if we take the set in which S, we take the whole W, then we get precisely W. Okay, so every subspace is the subspace of this kind for a particular choice of set. In this case, we take as a set the whole subspace W, seen as a set. Indeed, well, certainly this is included in W because W is a subspace. Therefore, any linear combination of elements in W still remains in W. Therefore, we have trivially this inclusion. Vice versa, the opposite inclusion we get expressing any element of W as a particular combination, linear combination of elements of W. So indeed, let a small w be an element of w, then we can express w as a linear combination of which vectors inside w? Well, we take just the unique vector w and we multiply by a scalar 1. Okay, so this is a linear combination of some elements of w, namely just w, multiplied by scalars. In this case, we just multiply by 1. That means that we also have an inclusion the other way around. We see now a few examples of these subspaces. So examples. Let's start from the most trivial one, which is if we take S to be simply one vector V. Okay. So in order to understand what this vector space is in this particular case, we have to understand what is a linear combination of vectors in S. Then, so we take linear combination as written here is going to be what? A sum from I of I that goes from 1 to n of elements of vectors of the kind lambda I times vi, but vi are all taken inside S. Now S has just one vector, therefore this sum reduces to the following: sum for I that goes to 1 to n of lambda I times v, because there is no other choice, there is just v inside here. Now this we can rewrite in the following way: sums for I that goes from 1 to n of lambda I that multiplies on the left v. So here we use distributive property of the product with respect the scalar product with the scalar with respect of the sum of scalars. Okay. So in particular, we can call this alpha times v for alpha in K. Okay, so this is a sum of elements in K, therefore is an element of K. So we notice that any linear combination of elements in S reduces to just v multiplied on the left by a scalar. So vice versa, any vector of the form alpha times v is a linear combination hence. So in this case we have that this vector space, which should be denoted as this, because the set S is just this, but for abuse of notation we'll just denote with, sorry, this is simply going to be the following set. alpha times v such that alpha is in K. Okay, nothing else. So these are just multiples of v. In this particular case, the set of all linear combination, the vector space of all linear combination, is just multiples of v by scalars. Okay, let's pass to the next simplest example, which involves taking S to be two vectors. Okay, so v1 and v2. Then, by definition, we have that the vector space S as a set is going to be lambda 1 times v1 plus lambda 2 times v2. Sorry. So are going to be these vectors such that lambda i's belong to K. Okay. So notice that this looks like being the same kind of set, regardless what v1 and v2 are. Okay. But in fact, is not exactly what it looks like. So notice that if v2 equals to alpha v1, lambda 1 v1 plus lambda 2 v2 can be rewritten as lambda 1 v1 plus lambda 2, and then we substitute for v2 this expression alpha times v1 alpha times v1. So this means that we can again use the distributive law with the multiplication of the scalars with respect of the sum of scalars. So we can rewrite this expression as lambda 1 plus lambda 2 alpha times v1. Okay, so in particular, it's going to be a beta times v1 for beta in K. The vector space generated by v1 and v2 in this particular case is the same as the set generated by just these linear combinations beta times v1 with beta in K, varying beta in K, which is precisely as we have seen in the previous example. This is precisely as the vector space of this form, where S is just v1, so in which we dropped v2. So in this particular case, where v2 is a multiple of v1, we end up getting that the vector space generated by v1 and v2 is just the vector space where here we take as S just v1 and we drop v2. So v2 does not give any contribution to this the vector space here. It is called vector space generated by S. So v2 does not give any contribution to the vector space generated by the set v1 and v2. More in general, so this is true more in general. More in general, if in v1 through Vn. Vj equals a linear combination for I different from j. So a linear combination of vectors different from j. So lambda I times Vi, then a linear combination of Vi's, of all these Vi's, for I that goes from 1 to n of lambda I Vi, equals to the linear combination for I different from j. So we just gather all the summands different from the jth summand here. So we take I different from j, lambda I Vi, plus we would have lambda j times Vj. But Vj has this expression, so we substitute to Vj this expression, and we get lambda j times sum for I. We plug this in Vj, this expression. Oh, there is lambda j here and lambda j here, so this is confusing. So let's assume that the scalars are different. So here we don't have lambda j, well, we just have, let's say, alpha i's. Okay, so Vj is a linear combination of Vi's with alpha I as a coefficient. Therefore here we have alpha i's and Vi's. Okay. Now you see, if we can commute the summands in order to have just V1 multiplied by the component of V1 here and the component of V1 there. Okay, so we will finally end up with the following sum: I different from j of Vi. Here the contribution is just lambda I, plus here every summand, since we can distribute lambda j to each of these summands, the coefficient of Vi is going to be lambda j times alpha I. So plus lambda j times alpha I. Okay. So, well, but this is just a linear combination with some coefficients in k of Vi's. So we can rewrite all of this as I different from j, beta I times Vi. So the bottom line of all these equalities is that any linear combination of all the Vi's reduces, in this particular case, when one of the vectors is a linear combination of the others, reduces just to a linear combination of the vectors different from j. Okay. So this implies, once again, exactly what happened before. So the vector space generated by V1, Vn, all of them, is exactly the same as the vector spaces generated by just V1, and then the Vj is dropped, and then we keep all the other ones until Vn. Okay?